All right, let's take a look at something called the first shifting theorem. The first shifting theorem is an incredibly useful theorem when we're talking about Laplace transforms. Here's what it says. It says if you're doing a Laplace transform of e to the at times f of t, so basically part of the function that you're doing a Laplace transform is an exponential. All that ends up doing is once you do the Laplace transform, this is going to be big F of s minus a. All that means is all you have to do is just do the Laplace transform of f, basically ignoring the exponential, and then replace all the s's with s minus a. Now this is easy to see because by definition, f of t will be the integral from 0 to infinity e to the negative st e to the at f of t dt. We can combine those two exponentials, that's e to the negative st plus at f of t dt. Now I'm going to do a little bit of factoring here. I'm going to factor out the negative, and this will be s minus a times t. Now notice this is almost exactly like our initial Laplace transform. Watch, I'm going to erase this real quick. Right, that's just a Laplace transform of little f of t, except we shifted the s to s minus a. So all this is just big F of s minus a. Okay, so it makes it very, very easy to do the Laplace transform if part of your function is an exponential. So let's see how we can apply this to a few examples. I guess we can leave it up there. So let's say if I said, what's the Laplace transform of e to the 4t cosine 3t? Well, since we're multiplying by an exponential in the t world, we know all that's going to be is a shift in the s world. So we're going to say all this is going to be is this is going to be a Laplace transform of just cosine 3t. But over here in the s world, we're going to place s with s minus a. So in this case, we're going to replace s with s minus 4. So from our table, if you haven't already kind of seen how this works, the Laplace transform of cosine of 3t will be, well, that'll be s over s squared plus 9. But now we have to replace all of our s's with s minus 4. So this will be s minus 4 over s minus 4 squared plus 9. So if you see, by multiplying by an exponential in the t world, it ends up just shifting all the s's in the s world. So all you got to do is transform the normal function and then replace your s's with the shift. So if I said, what's the Laplace transform of e to the negative 2t, t to the fifth? Well, what does that tell us to do? Well, since we're multiplying by an exponential in the t world, we know we're just going to do a Laplace transform of the function and then shift it. S to what? S minus a, where a is negative, so this is going to be s to s plus 2. So the Laplace transform of t to the fifth, that's going to be 5 factorial over s to the sixth by our definition. So this is 5 factorial over s to the sixth, but we got to replace all of our s's with s plus 2. So this is 120 over s plus 2 to the sixth. All right, so very, very helpful if you have an exponential as part of the function that you are doing the Laplace transform. However, most of the time this is very useful when we're doing the inverse Laplace transform, going the other way, which means this. Let's say if I ask you to do the inverse Laplace transform of 1 over s plus 3 to the third. So here's the thing. If you're in the s world, and everywhere you see an s, you see the same thing like s plus 2 or s minus 7, you're thinking that, hey, we can use our inverse Laplace transform in the first shifting theorem to help us. Because what basically happens? Well, this means that this was a multiple of e in the t world. So I can say that this was e to the negative 3t times the inverse Laplace transform of 1 over s to the third, right? Because this multiple in the t world would have given us our shift in the s world. Now what's the inverse Laplace transform of 1 over s cubed? Again, top right over there, our n here is 2. So let's see, this is e to the negative 3t. I need a 2 factorial on the top, which means I need a 2 factorial down there. This will be s to the third. So this is 1/2 e to the negative 3t. Since n is 2, this will be t squared. All right, so if you see a shift in the s world, basically everywhere there's an s plus or minus a number, you can pull out the exponential to make the function that you're taking the inverse Laplace transform of much easier to deal with. All right, let's do a much more difficult one here. So let's say we have, I ask you to do the inverse Laplace transform of s over to s squared plus 4s plus 5. All right, now we've seen this when we have a quadratic in the denominator that has that linear term, right? That's not like the sine and the cosine. The last time we said, well, if we could factor this denominator, then we could use partial fractions. This denominator won't factor. So if the denominator won't factor, what you need to do is complete the square for this. So I'll do it over here real quick sideways. So to complete the square, we're going to ignore that constant real quick. I'm going to add, then subtract half of the linear coefficient. See, now this will factor. This factors to s plus 2 squared minus 4 plus 5. So that's s plus 2 squared plus 1. So by doing that, I end up with a statement that looks like this. S plus 2 squared plus 1. All right, now when you see these binomials squared like this, you're really thinking that first shifting theorem because you have that shift. The problem is up here at the top, I don't have that same shift. To be able to use the first shifting theorem, and I want to use this plus 2, everywhere there's an s, I need an s plus 2. Well, I'm going to cheat to get what I need. On the top, I know I need an s plus 2, but I can't just add a 2 up there. I'd have to also subtract 2. This would be over s plus 2 squared plus 1. Now I'm going to keep the piece that I want. I want that s plus 2, and I'm going to break that piece over to the side, break it up into 2 pieces like we've seen in the past. So I'm going to write this as s plus 2 over s plus 2 squared plus 1 minus 2 over s plus 2 squared plus 1. All right, now since I have 2 pieces here, I can do the inverse Laplace transform of each term. So this is the inverse Laplace transform of s plus 2, s plus 2 squared plus 1 minus, and I'm going to go ahead and pull that constant out. It's normally helpful to pull constants out. S plus 2 squared plus 1. All right, now notice in each one of these inverse Laplace transforms, everywhere there's an s, we have that s plus 2, which means now I can use my first shifting theorem. So for this one, we can pull out basically e to the negative 2t, and then inverse Laplace transform, that's just s over s squared plus 1 minus 2, and again, since everywhere there's an s, we have this s plus 2, this is really e to the negative 2t times the inverse Laplace transform of 1 over s squared plus 1. All right, so now our expressions are quite a bit easier to do the inverse Laplace transform. In fact, the first one fits the cosine exactly. So this is e to the negative 2t cosine t. And inside this one, because the square root of 1 is 1, this fits the sine exactly. This is 2e to the negative 2t sine t. So if the denominator does not factor, completing the square to get it into a form is very, very helpful. That generally means you're going to use your first shifting theorem, because now you're going to have this shift. If you don't already have that same shift, add and subtract what you need and break the pieces apart. So first shifting theorem, very, very helpful theorem.